They say your body starts burning fat the moment you skip a meal. That fasting flips a switch. That stored fat immediately becomes fuel. But inside your body, energy use is not that abrupt. When food stops arriving, a sequence unfolds. Glycogen is accessed first. Hormones shift. Insulin falls, glucagon rises. Fat cells remain largely quiet at first. The liver adjusts. Muscle tissue changes preference slowly. Fat burning is not a dramatic ignition. It is a controlled transition on a rising tide within a system built for survival. The body follows hierarchy. It preserves balance. And yet subtle signals hint at the shift. When does your body truly begin relying on stored fat? After hours, overnight, or only when deeper reserves are required? To understand this transition, we must follow the hidden steps of metabolism. Let's begin. 1. The first hours without food. After the last bite is swallowed, digestion continues, but gradually, external fuel stops entering the bloodstream. For the first few hours, the body remains in a postprandial or fed state. Glucose from the recent meal circulates, insulin directs nutrients into cells, and energy is readily available. As time passes, blood glucose begins to decline. The pancreas detects this subtle shift. Insulin secretion decreases, removing the constant storage signal from the bloodstream. Cells begin to sense a changing environment. Muscle and liver tissue adjust their uptake, and energy demands start to outpace the immediate supply. The liver, a central metabolic hub, steps in. Stored as glycogen, branched chains of glucose lie in wait for such moments. Through glycogenolysis, the liver slowly releases glucose into the blood, maintaining a stable environment for tissues that rely heavily on carbohydrates, such as the brain and red blood cells. This early phase is characterized by careful balance. Energy homeostasis is maintained, not through dramatic shifts, but through gradual adjustments. Muscle activity, though low during rest, continues to signal minor glucose utilization. Fat stores remain largely dormant. Within these first hours, the body begins to reorient itself. Hormonal cues quietly prepare cells for the eventual transition to fat-derived fuels. The change is subtle. The metabolism is patient, deliberate. The body does not rush. It maintains a hierarchy, drawing first on circulating glucose and glycogen, preserving adipose tissue for longer-term energy security. The stage is set. The transition from short-term carbohydrate reserves to fat metabolism will unfold slowly, signaled by cellular sensors, enzymatic activity, and hormonal messaging. 2. Hormonal choreography. The switch from a fed to fasting state is orchestrated by a precise hormonal dialogue. Insulin, glucagon, cortisol, and adrenaline act as messengers, each influencing tissues and enzymes to ensure energy balance is maintained. As insulin falls, the inhibitory signal on fat cells diminishes. Glucagon rises from pancreatic alpha cells, signaling the liver to release glucose and prepare for alternative fuel production. Cortisol contributes by promoting gluconeogenesis, generating glucose from amino acids and other substrates. Meanwhile, low-level adrenaline supports glycogen breakdown in the liver and muscles, maintaining blood sugar for essential functions. Muscle tissue, once flooded with insulin signals, gradually reduces glucose uptake. It becomes more receptive to oxidizing fatty acids when they become available. Meanwhile, the brain continues to prioritize glucose, receiving a carefully regulated supply from the liver. This hormonal environment is coordinated, not chaotic. Each messenger operates in rhythm, responding to declining blood sugar, feeding cues, and energy demand. The liver, muscles, when and fat cells interpret these signals, adjusting metabolism incrementally rather than abruptly. By the time the first hours of fasting pass, the body is primed. Glucose continues to circulate, glycogen is deployed methodically, and fat tissue remains largely dormant. Hormones quietly establish the groundwork for eventual lipolysis. The system is adaptive, hierarchical, and precise, ready to shift to longer-term energy sources when carbohydrate reserves decline. For 3, glycogen before fat. Before the body significantly taps into stored fat, it relies on glycogen. Liver glycogen acts as a short-term buffer, maintaining stable blood glucose during fasting. Muscle glycogen, while more abundant, is generally reserved for contraction and localized energy use, not systemic glucose supply. In a well-fed adult, liver glycogen stores roughly 80 to 120 grams of glucose. These reserves can maintain blood sugar for several hours, depending on activity and prior diet. And during this phase, fat oxidation is minimal. Muscle and liver cells prioritize carbohydrates because they are energetically efficient and immediately accessible. Even as fasting progresses, fat cells remain restrained. The body conserves adipose tissue for periods of prolonged energy scarcity. Meanwhile, peripheral tissues gradually adapt, slightly increasing fatty acid oxidation, but this is supplementary rather than dominant. This hierarchy ensures survival. Carbohydrates are fast, accessible, and protective of vital organs. Fat is abundant but requires mobilization, transport, and enzymatic conversion before it can be used efficiently. The delay in fat utilization reflects an evolved strategy to prevent unnecessary depletion of long-term energy stores. Only as liver glycogen diminishes substantially does fat mobilization accelerate. The body transitions gradually, signaling through enzymes and hormones, ensuring tissues never experience abrupt energy shortage. When the early fasting hours are a period of measured conservation, guided by glycogen, maintaining equilibrium while preparing the stage for fat-derived fuel. 4. Initiating lipolysis. After several hours of fasting, hormonal and enzymatic signals converge to activate fat metabolism. Fat cells, or adipocytes, contain triglycerides, long-term energy reserves composed of glycerol and 3 fatty acids. These molecules are metabolically dormant during feeding, restrained by insulin. As insulin remains low and glucagon rises, hormone-sensitive lipase becomes active within adipocytes. This enzyme initiates lipolysis, breaking triglycerides into free fatty acids and glycerol. The fatty acids bind to albumin and travel through the bloodstream to tissues like muscle and liver, where they enter mitochondria to undergo beta oxidation, producing energy. This transition is gradual. Small amounts of fat oxidation can occur within 12 to 24 hours of fasting, but glycogen continues to provide the bulk of circulating glucose. Gluconeogenesis still supplies critical tissues, especially the brain. Fat burning is a rising tide, not a switch. The metabolic system shifts cautiously, ensuring energy balance remains stable. Cells adjust substrate preference incrementally. The liver may begin producing ketones if fasting extends, but this deeper adaptation arrives only after carbohydrate reserves wane further. By the end of this stage, the body has begun unlocking its long-term energy stores, guided by hormonal signals, enzyme activation, and cellular readiness. Lipolysis is underway, a measured step toward the body's adaptive transition from glucose to fat fuel. 5. Ketones and deeper fasting. As fasting extends beyond a day, the liver begins a new metabolic process, ketogenesis. Free fatty acids, released from adipose tissue through lipolysis, flood the bloodstream. When the liver oxidizes a portion of these fatty acids for its own energy needs. When supply exceeds immediate demand, the liver converts them into ketone bodies, acetoacetate, beta-hydroxybutyrate, and acetone. Ketones are compact, water-soluble energy packages designed for transport. They circulate to tissues including the brain, heart, and muscles, providing a versatile fuel source. The brain, typically dependent on glucose, gradually adapts by increasing transporter expression at the blood-brain barrier. Over time, ketones can supply a substantial portion of cerebral energy needs, conserving glucose for tissues that cannot use fat directly. This shift is gradual. Detectable ketone levels may appear within 12 to 24 hours, but significant elevation typically requires longer fasting periods. The rise in ketones signals that carbohydrate reserves are low and fat-derived energy is taking a larger role. It is not a state of emergency. It is a controlled adaptation. Cells and organs respond incrementally. Mitochondria, the energy-producing organelles, increase beta-oxidation activity. Gluconeogenesis continues to supply glucose for red blood cells and certain neural tissues. The body demonstrates metabolic flexibility, a seamless transition from short-term carbohydrate use to longer-term fat-derived fuel. Ketones, therefore, are not the start of fat burning. They are a marker of deeper fasting. They reveal the system's adaptation, showing that the body is carefully reallocating fuel while maintaining energy stability and homeostasis. 6. Myths of instant fat burn. A common belief is that skipping a single meal triggers immediate fat loss. In reality, the process is far more nuanced. Early fasting hours primarily rely on glycogen stores for energy. While small amounts of fatty acids may be oxidized, adipose tissue remains largely preserved. Fat oxidation refers to the burning of fatty acids for immediate energy, whereas fat loss implies a sustained reduction in stored triglycerides. The two are not synonymous. Temporary increases in fat oxidation, such as those occurring after 12 to 24 hours without food, do not equate to measurable body fat reduction unless repeated consistently over time within an overall energy deficit. The body is designed for energy efficiency and conservation. Hormones such as insulin, glucagon, cortisol, and adrenaline adjust dynamically. Energy expenditure may slightly decrease as the system adapts to fasting. Muscle and liver tissues switch substrate preference incrementally, prioritizing stability over immediate depletion of fat stores. Misconceptions arise from oversimplification. Fasting triggers mobilization of stored energy. Yes, but meaningful fat loss is cumulative. It depends on duration, frequency, metabolic health, and total energy balance. Skipping one meal is a temporary adjustment, but not a metabolic reset. Understanding the distinction between early fat oxidation and long-term reduction emphasizes the body's strategy: gradual, deliberate, and protective. Fat stores are released with caution only when carbohydrate reserves decline and hormonal conditions favor sustained utilization. 7. Long-term metabolic adaptation. Repeated fasting episodes create lasting changes in metabolic function. And cells become more adept at switching between glucose and fat as fuel, a trait called metabolic flexibility. Mitochondria, the cellular powerhouses, increase capacity for beta-oxidation of fatty acids. Enzymes governing lipolysis and ketone production are upregulated, improving efficiency. Insulin sensitivity often improves. The body requires less hormonal effort to move glucose into cells after meals, reflecting refined cellular signaling. Liver gluconeogenesis becomes more regulated, balancing glucose output with rising ketone production. These adaptations do not lock the body in a permanent fat-burning state. Instead, they enhance responsiveness, enabling smooth transitions between feeding and fasting periods. Hormonal systems adapt to repeated patterns. Glucagon, cortisol, and adrenaline responses become more predictable, reducing extreme fluctuations in blood glucose. The liver, muscles, and adipose tissue coordinate more efficiently, optimizing energy allocation. A metabolic adaptation is individualized. Genetics, activity level, prior diet, and overall health influence the degree of improvement. Over weeks and months, repeated fasting strengthens the body's ability to switch fuels without significant disruption, conserving energy while supporting prolonged metabolic stability. In essence, the body learns through repetition. It refines enzymatic pathways, calibrates hormonal responses, and enhances substrate flexibility. Long-term adaptation is a slow, cumulative process reflecting the system's capacity for optimization rather than immediate transformation. 8. Reading the body's energy signals. Fasting communicates with the body through physical sensations. Hunger rises in waves tied to circadian rhythms of ghrelin, the hunger hormone. These waves indicate timing cues rather than actual energy deficit. Early fasting energy dips correspond to declining blood glucose before ketone production ramps up. Since some individuals notice increased mental clarity after several hours, others feel temporary fatigue. These shifts are biological signals of substrate transition, the brain adapting to partial ketone availability, while peripheral tissues begin oxidizing fatty acids. Cold extremities may reflect reduced thermogenesis as insulin declines and metabolic rate slightly adjusts. Pulse, mild heart palpitations, or subtle weakness can indicate changes in circulatory demands as the body reallocates energy. Muscle efficiency and glycogen usage are adjusted, reflecting deeper fuel transition. These signals are not warnings of harm, but indicators of metabolic recalibration. By observing these markers, hunger, energy fluctuations, mental clarity, and physical sensations, we can infer where the body stands along the continuum from glucose reliance to fat oxidation. Fasting is not silent. It communicates through waves, pulses, and shifts in energy availability. The body does not rush into fat burning. While it transitions carefully, guided by hormones, enzymes, and cellular preference. Every signal is a reflection of fuel hierarchy. Glucose first, glycogen second, and fat when carbohydrate reserves decline. The system is deliberate, protective, and resilient. Fasting is not a sudden switch. It is a measured sequence of metabolic events, orchestrated by enzymes, hormones, and cellular preferences. From glucose circulation to glycogen breakdown, from lipolysis to ketone production, the body transitions deliberately, preserving energy and maintaining stability. Every hunger wave, every dip in energy, every subtle shift in mental clarity is a reflection of this internal choreography. Understanding these signals allows insight into how your body prioritizes fuel, balances demand, and protects its reserves. Fat burning does not occur instantly, but gradually, guided by hierarchical energy allocation and metabolic flexibility. The system is adaptive, resilient, and remarkably precise. This channel explores the science behind everyday physiology, revealing the hidden processes that shape health and energy. If this exploration deepens your understanding, consider subscribing for more evidence-based insights into how your body truly functions. Share your observations and questions below, and stay tuned for the next detailed journey into human metabolism. Inside every hour without food, a quiet, precise story unfolds. Metabolism in motion, silent yet measurable, revealing the remarkable design of the human body.